Hello everyone, my name is Hui Luo from MIT University. Today I'm going to present our paper, Facility Relocation Search for Good, when facility exposure meets user convenience. The topic of this paper is facility relocation. Given a set of users, a set of existing facilities, and a set of potential sites, we decide which of the existing facilities to relocate to potential sites, such that two factors are satisfied. The first one is facility exposure. That means facilities after relocation should have balanced exposure, namely serving equivalent numbers of users. The second one is user convenience, because it is convenient for users to access the nearest facility, which provides services with shorter travel distance. Here comes one motivation example in Figure 1. Figure 1 illustrates an example before and after facility relocation. Initially, in Figure 1a, there are three users, U1, U2, and U3, two existing facilities P1 and P2, and two potential sites L1 and L2. The potential sites are ideal locations for existing facilities to relocate to. Following the closest proximity principle, it is clear that P1 is the nearest facility for all three users, while P2 is unused. In Figure 1b, when we move P2 to L1, L1, which is actually the raw P2, becomes the nearest facility of U1 and U2. In such a way, users have shorter travel distance and there do not exist idle facilities. This problem is motivated by applications such as dynamically redistributing vaccine resources to align supply with demand for different vaccination centers, and relocating the bike-sharing sites daily to improve the transportation efficiency. Here comes the problem definition of this research question. We have a set of input, that is a set of users U, a set of existing facilities P, a set of potential facility size L, where a new facility can be built, and a parameter alpha. The output will be a set of new facility locations. We formalize this problem as the following optimization problem in this equation, which we aim to minimize the function O. When we define the objective function, it includes two kinds of goals. The first one is facility-related goal, which we aim to minimize the difference between one facility's exposure and the average exposure. The second goal is user-related goal, OU, which aims to minimize the total average travel distance of all users. The facility relocation problem can be reduced to 0-1 integral programming, which is a well-known NP-hard problem. And in our solution, we have proposed two kinds of algorithms. The first one is a long learning best response algorithm, which we call it as BR. We cast our problem as a multiplayer game, where each player selects their own strategy to achieve a global objective. In such a way, we will find the Nash equilibrium to balance the facility-related goal and the user-related goal. We will terminate the algorithm when no further facility relocations are acceptable. Otherwise, we will violate the Nash equilibrium state. To avoid being confined to only one Nash equilibrium, we propose a second algorithm, that is, a reinforcement learning algorithm, which allows more search space to be explored, where considering continuous facility and potential site selection on either facility or potential site is also Markov decision process. We learn to decide whether a facility will be relocated or not. In our experiment, we have used two real data sets. The first one is from Victoria, Australia. It will include the lottery properties and GP locations. Therefore, the user data will be based on the real estate location, that is, users' home locations. For the facility data, we will adopt the GP locations, which is extracted from the Health Engine Australia. We also use another public dataset in New York City from Foursquare check-in dataset. We will extract all unique facilities and use their locations. Finally, we got a total number of unique facilities. Additionally, we use the following metrics to evaluate our experiment. We have two kinds of ways to evaluate the effectiveness. The first one is goal aspect, which include facility-related goal OF and user-related goal OU. And the second aspect is from the benefit. We will expose the mean travel distance of users and generalize the entry pay index of facilities. Here, the GEI is defined in the following equation. The smaller the GEI value is, the more fair the exposure among different facilities will be. Our result can be found in the following figure after comparing with the state-of-the-art algorithms. This figure has shown the goal aspect effectiveness, which includes the report of the OF and OU. If you find the figure, you can find our proposed method RL achieves 39% smaller O than GR when the number of users is 30,000. Another result is from the perspective of benefit. We can observe that our proposed method RL achieves 14% smaller mean travel distance and 50% smaller GEI than GR when the number of users is 30,000. If you have any question, please feel free to send an email via the following email. Thank you very much.